Great. Okay, good. So welcome back. We're doing module 9 today. This is, so we have 2 more modules that basically teach you new theory. We're going to do module 9 with correlation and linear regression today. We're going to do multivariable regression and the interpretation of multivariable regression next week. Both of these topics today and tomorrow and next week will be important for your final project, because essentially this is just a wonderful way to approach correlational analysis. I will also post for next week a video of me explaining logistic regression, and I will post the respective slides that you can choose to utilize logistic regression as well. You will see in these explanations what this entails and why logistic regression is hypothetically also a method you may consider. So, but let's focus on these 2 aspects first. So we're talking today about linear regression, correlation, and simple linear regression. It's basically 2 variables that are being associated. It's 2 variables that are continuous in nature, as opposed to earlier analyses where we did hypothesis testing, where we basically have a dependent variable that is continuous in nature, and we have an independent variable that is a categorical variable. So if you have a categorical variable with 2 levels, so let's say control group and treatment group, or diabetics and non-diabetics, that is counted as an independent variable, you do hypothesis testing using a t-distribution, for example. You use an independent sample t-test for these 2 distribution. If you have 3 or more variables or 3 or more levels of the independent variable, you would use an ANOVA, right? If you have 2 categorical variables that you want to test for an association, you would do a chi-squared test, as we done last class. If you have 2 continuous variables and you want to test these 2 variables for associations with each other, then you use correlation. And correlation essentially is just a first step towards regression. So correlation basically just tests for the associations between these 2 variables. So just in the same fashion as essentially the chi-squared, we just can make the conclusion, and we can draw the inference that there's an association between these 2 variables. Regression brings a correlation then on the next level, where you essentially can utilize the independent variable to predict the dependent variable. And this is where the equation that we will be deriving today, the regression equation, important because you can numerically utilize this for prediction. So you can literally predict an outcome variable, a dependent variable. We will play around today with this a little bit. And next week, we're going to go on the next stage, on the next level, we're going to do multivariable regression, where basically you don't use only 1 independent variable, but you use several independent variables at the same time to predict 1 variable, 1 dependent variable. We have practice lab 9 today. A discussion topic was posted. Next week, we're going to do practice lab 10, a little quiz again, and yeah, discussion topic 10 is due. Analysis plan, and final project first draft. I will get your comments back ASAP. I will review your drafts, and I will give some recommendations. And I hope you also made progress with the data camp exercises. I hope this is going well. Any problems with the data camp exercises? Is that going along? All right. So. Okay, no, but it's important that you finalize this before you really finalize the code for the final project, because there are good exercises in there. So it's data camp. I really like the platform. Essentially, it's very, very useful. Okay, any questions concerning the syllabus, concerning assignments? I think it's quite well mapped out, I hope, in the syllabus. Good, then we can now start with some theoretical, some background of what we're discussing today. So this is consistent with open interest at chapter 8. We're talking about simple linear regression and Pearson correlation coefficient and the coefficient of determination, which is kind of a way to quantify linear regression and its accuracy. So basically, we have a response or an outcome variable, and we have an independent variable that acts as a predictor. So there are different ways of how you basically look at regression model. You can either look at it in a predictive way and fashion, where basically you include several variables and you just see whether there's a signal in there that basically associates independent variable with the outcome variable, or you try to build an explanatory model where you really try to find independent variables that allow for you with a certain level of accuracy to predict the outcome. So these are two different paradigms in how you build your models. It will basically then be different in terms of how you select your independent variables. So for explanatory models in particular, you would use a rationale where you include the respective parameters. So in epidemiology, you would also use and you would map out directed acyclic graphs, so-called DAGs, that basically allow for you to really kind of visually depict associations between variables. Then you would individually look for the association between specific variable pairs, and you would map these associations out, and then based on these associations and the underlying physiological, pathophysiological, sociocultural, and socioeconomic correlation, you would basically include then these variables in your model. So it's hand-selected and rational-driven inclusion of independent variables. So basically, the inference is then done on the response variable. So you have an outcome variable and you have a given outcome, and you try to draw inferences based on whether the predicting variable or the independent variable is significant in your model. And this we will do by reviewing the interpretation of different models to the end next week. What is important whenever you're plotting a correlation, and we will do a scatter plot today. We've done a scatter plot before. When you do a scatter plot, which is basically the basis of all correlational analysis, because you're mapping out and you're displaying your dependent variable on the y-axis as a function of the independent variable on the x-axis. So important is that you keep with the nomenclature and the traditional approach that on the y-axis you have your dependent variable, your outcome variable, and on the x-axis you have your independent variable. And in essence, whenever you look at graphs, it's kind of always in that fashion, right? If you think, for example, about a box whisker plot, you have the dependent variable on your y-axis, and you have two categories, or more categories for an ANOVA approach or for an independent sample t-test approach. You have two categories then on the x-axis. So it's the same principle. So you have the dependent variable on the y-axis and your independent variable on the x-axis. And this is this is consistent to interpret it that way. So we have drawn inferences for two categorical variables. We've done the chi-square test. We have quantified these categorical variables with contingency tables that basically showed the count in the respective category, where these two variables, those two categorical variables come together. And by that, we estimated the expected count based on the so-called marginal totals. So we utilized this essentially to estimate our left top cell and then populate the rest of the cells as the difference to the marginal totals. So this is how you fill a frequency table, and then you can basically utilize this to compare this to your observed counts, and the difference between those will then basically lead you to quantifying the chi-squared. That essentially will allow for you to determine whether there is an association or not. And that will lead you then to post hoc analysis, as well as to more detailed analysis where you can quantify odds ratios or risk ratios with binary variables. Of note, odds ratios, or particularly odds ratios and risk ratios, can also be estimated. And these odds ratios are, for example, with logistic regression, you're estimating an odds ratio. So this is actually, this is not like a multivariable regression, a model where you predict a dependent variable. You're predicting with a logistic regression a binary outcome, which is either yes or no. Either the patient died or not. Either the patient was in the hospital or not. So you're quantifying a probability or the odds of an event to happen or not. And remember the difference between probability and odds. Probability is between 0 and 1. So you have a probability ranging from either it doesn't happen, then it's 0, or it does happen, then it's 100%. And odds is basically dividing the probability of an event occurring over the probability of the event not occurring. That's basically, it's for rolling a die, it would be 1/6 is the probability, and 1/5 would essentially be the odds. So, okay. So this is odds ratios and risk ratios. Also, risk ratios can be modeled with models. So this is the second one in the realm of probabilistic models. They could be done, for example, when you quantify risks over time. As an example, for example, you could do this with a hazards function model, so a proportional hazards function model, like a Cox regression. But that's different conversation piece. Good. Okay, so if inference and description for two variables, we have a continuous response with a categorical predictor. That would be done either with a t-test or an ANOVA. For the final project, and just in general, when you really want to predict these nicely, that's best done with a box whisker plot, which basically shows you also a distribution in some shape or form. When we're looking at two variables that are continuous in nature, you would basically use a scatter plot. And this scatter plot basically allows you then to determine this correlation visually, and then numerically quantify it with a correlation coefficient in correlation, and then in a predictive fashion, you can use it for regression analysis. We'll predict the y-axis utilizing the x. So the examples are quite frequent. So there are many examples. So you can, what you always need to look for, you basically look for what is the dependent variable and what is the independent variable. So you would utilize this essentially by quantifying one variable with another variable. What you often find in terms of terminology is that you find either a positive or a negative correlation, or you find a positive correlation and an inverse correlation. So this is quite common nomenclature and terminology that is being used. Here again, so here you see, for example, how you would show this in a scientific paper. So you can show if you have here quality of life associated with other parameters. So quality of life is actually, I don't know who of you is familiar with quality of life surveys. They're getting increasingly, well, I wouldn't say popular, but they're getting increasingly frequently used. And in our dialysis population, for example, there is a requirement to actually test this once a year, and you basically quantify quality of life in your patient. It's a self-reported measure of how well am I doing, how well am I dealing with my disease, what's my general perception of health. So there are various dimensions quantified in there that basically allow the physician to understand what is this self-perceived perception of health and disease. So one way how you could predict, how you could report this would basically, so you determine the significance of the correlation, and we'll talk about this today, how you do that. And you're presenting here the so-called R. And the R basically stands for the correlation coefficient, and that's the strength of the association between these two variables. Ranges from a value from -1 to +1. And the closer it is to -1 or, yeah, the closer it is to -1 or +1, the stronger the association will be. Yeah. So here we have also quantified this correlation with a p-value. Yeah. Okay, scatter plots are used for this visualization. Correlation is then used to quantify the strength. Notably, correlation in the context we're discussing it is only quantifying linear relationships. So non-linear relationships, that's a whole different ballgame. That's quite a bit more complex, and can also not be done by hand. Linear relations you can almost calculate it by hand. And if one of you is interested, we can go through the arithmetics. It's actually pretty fabulous arithmetics. What is important is the last statement here. And who said it on the discussion topic? Natanya, I think it was you. You said correlation doesn't equal causation. And I like that you kind of, you broke that down there, because it is often mistaken that correlation indicates a causal relationship. And this is in many cases not true. And this is where my spiel before about DAX comes into play, because this is why we're doing these directed acyclic graphs, and this is why we're putting so much thought work into these associations, because if you implement a variable in a model, this has ramifications. And if you only do this based on an association that you're not even sure has any physiological or pathophysiological relevance, you're basically overfitting your model based on grounds that will essentially lead you more likely to a tattoo error than anything. So it's important to keep in mind that just because there's an association, that doesn't mean it's necessarily a causal relationship. Causal relationships can only, causal relationships in the end of the day can only be established by randomized controlled trials. When you want to understand if a difference between two groups is indeed conferred by the differences between that group, whatever that means, you need to quantify this in an unconfounded manner. That means if you have two groups and they're randomized to each other, the distribution of all known factors as well as the unknown factors is equal. That means you can exchange individuals from either group and the distribution doesn't change. There's in trial design called equipoise, and there's actually super central to trial design. But you're learning all of this like right after that class, right? So this is the only way how you can quantify causal relationships. However, and this is the epidemiologist in me wants to show you that. So there was a former CDC director, I think he was, Bradford Hill. He quantified how you can, with an increased certainty, quantify causal relationship, even if you only have retrospective data, epidemiologic data. And this is in epidemiology handled as quite of a guiding star when you do analyses. And this is a review on his work. And you have here the factors that basically will lead to you gaining more certainty about your associations. So I encourage you to really read this paper in much detail. I will not go into much detail into it. I'm just going to pick a couple of them. So for example, consistency. If you do this analysis in different populations and you see a consistent signal, you're kind of getting a little bit more confident, not certain, but confident that hypothetically you're onto something, that this association that you see is indeed a relevant causal relationship. There's no certainty, but you gain more insight into the dynamics in different populations that will lead you to be more confident about it and more likely to be able to propose this as a prospective research project. Another one is the specificity. Is it a specific association that you're seeing? Is a specific relationship that is specific to an interplay between two variables? Temporality is the one association before the other association. So you basically look whether there is a temporal relationship that establishes or supports an association between these two variables. All quite logically, but really nicely laid out here. Then you have biological plausibility. Biological plausibility, or biological gradient first. Biological gradient is that if it's like a dose-response relationship, right? So you have more of one variable, will the other variable increase, and how strong is this relationship? How consistent and how reliable is this relationship? Then you have plausibility. That's where all these phase 1 trials come in. This is where this bench research comes into place. Has this been sufficiently established? And is this actually plausible to see in a large population what we see on a bench analysis? What else we got? Coherence. That's the cause and effect interpretation. Then is it consistent with an experiment? Are there analogies to other variables that are comparable to each other? So these criteria basically lead you closer to having confidence about the causal relationship. It's an interesting read. So I encourage you to have a look at that, but it's not part of any quiz. But for your final project, it could be interesting that you kind of do the analysis in different subsets, or you randomly sample different subsets and you repeat the same analysis, for example. So you have a sufficiently large data set and you could do repeated random samples, right? And it could be nice to kind of establish some certainty about your insights and the dynamics you're reporting. Okay, so we have linear and not any questions about any of this so far? All right. Okay, so we have linear relationships and we have nonlinear relationships, as the name implies. One is basically you're fitting a line through, as we have done in the past, as we will do today again. The regression models and the correlation basically describes linear relationships, but there are also nonlinear relationships that basically form a mathematical function. Becomes a little bit more complex to fit, becomes a little bit more complex to deal with arithmetically, interpretation-wise, coding-wise, and it's a whole different animal. But the most commonly used approaches are basically linear relationships, and that's what you do in most, how should I say, in the simpler research of epidemiology and medical research. You also have differences in the strength of a relationship. Obviously, if something associates perfectly between an X and a Y, you would expect this, irrespective of the actual numerical magnitude, you expect this to go exactly through this line of identity. That would be a perfect relationship. And the weakness essentially, the strength of a relationship can be either weak or strong. The stronger it is, the narrower this band around the points will be. And the weaker the relationship is, the wider this band will be. Makes sense, right? If you have no relationship at all, it's important that when you test for relationships, you're essentially testing against a null hypothesis that your association is basically a flat line. And you're essentially testing against the null hypothesis of a mean of Y. So it's a mean. So you're basically testing with regression analysis, you're testing against the null hypothesis that Y, so the dependent variable, can be predicted as accurate with just quantifying the mean as compared to that function that you're fitting through. So you're basically testing against the flat line as your association.
So this second one is
this is zero relationship. That's like null. That's like literally no relationship at all. Where correlation is also quite important is essentially, so you remember how we distinguished between mu and X bar, so sample mean and population mean, and sigma and S or SD, so standard deviation in a population, mean in a population, and mean in a sample or standard deviation in a sample. You're doing the same when you quantify either an R as the correlation coefficient or a so-called rho. Rho is basically the Greek letter for R, and basically quantifies a correlation in a population. And you will use rho when you literally have population data. So here, for example, you see children immunizations in kids, and you've built an association between those that were the percentage of immunized children and the under 5 years mortality rates, and that would basically give you a research example that you would quantify within rho. But basically follows the same outline. So each individual point here is one of these countries. And the beauty of a scatter plot is not only that it allows you to quickly quantify associations, it serves as a very useful descriptive way to describe your data. Because basically, if you're aiming for a correlational analysis, you can identify each of these countries essentially on your scatter plot. So the only thing you need to do, you need to understand what your independent variable is. If it's percent immunized, let's search for one of the more, okay, so that one is not a good one, that's not even on here, which is actually an interesting case because, oh no, it is 13 and 208. So if you have Ethiopia here with 13% immunized children and a mortality rate of 208 per 208 per, not clear what, so this is also when you have rates in a population health study, you would standardize it to a population. So if you have a certain rate that you have over time, you would standardize it to a population, to a fraction of the population. So likely this is quantified to either 100,000 Ethiopians or 1 million Ethiopians, but essentially you would standardize it to a certain population number. So this would be Ethiopian, and then you can basically find the same, taking one of the higher ones. Which one is the highest one? That's 99, Czech Republic. That would be this one, that would be Czech Republic. So you can locate individual points on your graph. So nobody joined on Zoom? No. Okay. Good. So this is what I said before, population correlation coefficients. That's just for both cases, it's an association between two continuous variables. The difference is sample or population. And in a sample, you also call it Pearson's correlation coefficient or the product moment correlation coefficient. So when it comes to the calculation of this, so we talked about that this is considerably easy. So essentially what you have just like in the past when we did ANOVA, for example, we quantified the sum of squares, right? Here we're not quantifying the sum of squares, we're using the direction. So you need to square when you calculate the standard deviation, for example, you need to square it because you want to take out that information of the direction. So if you're subtracting an individual point from a mean, you basically get either it's greater than the mean or it's smaller than the mean. So you get a direction of this difference. It's either positive or negative. So for the case of a correlation coefficient, you actually want to preserve this direction. That's why you don't square it. And you want to preserve it because you want to quantify with one number, which is a correlation coefficient, whether this is a positive correlation, where the dependent variable increases with the independent variable, or an inverse correlation where the dependent variable decreases with an increase of the independent variable. So you do this by basically quantifying the difference between each individual x, so xi, from n to I. So I equals 1, that's point number 1, to n, so where I equals n. So this means the entire sample size. So you're going through each individual data point and you take each xi and you subtract it from the constant x bar, that's your sample mean. You divide it by your standard deviation, your sample standard deviation. You multiply it by the difference of each individual y minus the mean of y. You divide it by the standard deviation of y, and you build a product. And then you basically get, for each data point, you get a product because between the difference divided by the standard deviation of x and y. And you build this product and you sum all these products up. And then you get the sum of the products. Then you divide this by the degree of freedom. That basically gets you to the correlation coefficient. And this preserves, because you're not squaring it, preserves your direction. So if it's tilted towards the x, there is gonna be basically a tilt in that direction, and this will give you a more negative value. And then you get a negative correlation coefficient. So these are examples, for example. So if you have positive relationships, your dependent variable increases with your independent variable. That's quite intuitive. And if the R is negative, your dependent variable decreases with the independent variable. And if it's 0, it's a flat line corresponding with the mean of y. So because of the way it's calculated, it's unit free, so it doesn't have a unit. Not like, for example, the standard deviation, where we determine the standard deviation and the mean. They basically have the same unit as the original variable. The correlation coefficient does not have this. Essentially, you're dividing this out by dividing the mean difference divided by the standard deviation. That's how the units drop out. And then you're left with a unitless number that associates both. So the closer to -1, the stronger is the negative relationship. The closer to +1, the stronger the positive linear relationship. The closer to 0, the weaker it is. So the other way you can look at it, so the absolute magnitude of your correlation coefficient will basically determine the strength of your association, disregarding the direction. High correlation does not necessarily imply linear relationships. High correlation do particularly not imply causal relationship, and are unfortunately also very sensitive to outliers. Because why? Because when you think of how it's being calculated, if you have outliers in there, so firstly it will affect your means, and thereby it will definitely skew your relationship in a direction you don't want to have. And you have, and we'll talk about this with regression, you have a phenomenon in this arithmetic approach that is called the regression to the mean. That means if you have outliers, they will change your mean. And as soon as they change your mean, the mean is very, very sensitive to outliers. As soon as they change the mean, this whole difference will be different. The standard deviation as well, but less so, but the mean is really pulling your estimate away in its direction. So null hypothesis is logically that there's no correlation, but rho equals 0. The alternative hypothesis is that it's unequal to 0. The distribution of a correlation is t distributed with degrees of freedom. Notably, you have one dropout, so one of these redundant variables, just like with the independent sample t-test, where you have two groups. Equally, you have here two variables, and you can leave one of these out. So you basically have your degrees of freedom is the sample size minus 2 rather than 1. Yeah, so I talked about Bradford Hill. That's just a quick reference to that. So this is where this fits well nicely into it. Any questions to correlation? I think it's considerably simple, right? And you certainly have heard that in earlier education. But just as a quick review. So now when thinking about regression, you're basically carrying correlation on the next level. So you're predicting now your outcome variable. So you predict the dependent on the value of at least one independent variable. and notably also explain the impact of changes in an independent variable on the dependent variable. So you can, what does that mean? So if you have an dependent variable and independent variable on the x-axis, you can estimate what the change in your dependent variable will be with a change in 1 unit of your independent variable. So if you build a relationship between, let's say, blood pressure and weight, you can quantify on the x-axis with weight the change in blood pressure with an increase of 1 kilo in weight. And this is the slope that we will be looking at in a second. Depending on the variable we wish to explain, and the independent, which is used to explain it. So in simple linear regression, there's only one independent variable x, and the nomenclature is that this is basically shown with uppercase X and Y for random variables. And if you talk about individual observations and equations, you look into you're using lowercase x and y. And that is a regression function. So basically, you have in a regression function, you have several important factors. You have a dependent variable. This is an uppercase y. That is your outcome variable. Then you have your intercept. The intercept in a regression plot or in a scatter plot is, where do we have a scatter plot? Here. Your intercept is where the regression function that you fit through your data, through your scatter, goes through the y-axis where x equals 0. So that is the intercept. The slope, which is the next variable, the slope, beta 1 as being the first variable, only variable included. That is basically your increase in the dependent variable with an increase of your independent variable. So that would be, going back to this. Let's say this is blood pressure as a function of weight. You have an increase in weight for one, actually that would be rather here. You have an increase in weight of 1 kilo. The increase here in the y value would basically be your slope. So that's the increase with 1 unit change of the independent variable. Then you have the independent variable capital case X, and then you have the random error. And the random error, that's a fascinating, that's essentially a fascinating component of this, because this is a normally distributed value that basically distributes with known variance, normally distributed around a mean of 0. Why? Because you're fitting this line here through a scatter. And with the simplest approach, you're fitting it with a method called least square approach. So you fit using a least square, ordinary least square estimation of that line. And this basically uses a minimization of the points, the individual points to your line. And by this minimization, you create a mean of 0 arithmetically. I spare you the arithmetic details. But basically, so this is the random error. This is the residual. That's the distance of each individual data point from your line. And so there are alternative ways how to depict it. But basically, what's important to know, whenever you look at a regression function, these will be the factors that you basically are seeing. And this is what you will be seeing in the output. Any questions on this? Well, this is an alternative way to look at it, which you also will see quite frequent. So you have a y hat, and your y hat is basically your predicted y. So this is when you have a model, you basically can utilize this model to predict values. And if you have an estimate of the intercept and an estimate of the slope, and you have an individual x, you can basically predict your dependent variable utilizing the regression function. Okay, So we're talking now about estimates of the intercept and estimates of the slope, and then estimates of the predicted y. So in R, there's actually, it's quite elegant how you can utilize this to predict, and you can basically use this function. Once you develop such a function on a population level, particularly with multivariable regression, you can utilize this multivariable regression to literally predict an individual. So let's say you have several variables in there. You have age, gender, I don't know, socioeconomic status, diabetes. You have all these individual entries for one individual. You can utilize this regression function to estimate the blood pressure for that individual. So you can literally estimate the numerical value for individual or simulated entries. So this is the least square. Just briefly about this. So again, the regression function is fit in its simplest form with an ordinary least square approach. So you're minimizing the distance between your individual data point and the regression line. And these residual actually are subject then to interpretation, because essentially they are supposed to be normally distributed. They're supposed to be homoscedastic. That means there's no increase in that residual error with a magnitude increase of x. And it means to minimize the sum of this residual. So that's how this line is fit. That's least squares, least square fitting. So B0 is the intercept. So this is where the average value of y when the value of x is 0. B1 or slope is the estimated change with 1 unit change in x. And so you have now a leftover error, right? So if you have your least squares, you will have residuals, you will have error. And this error is now basically subject of more detailed investigation. So any questions on least square fitting, regression? I think it's yes.
Is it possible to do the regression?
Sorry. What?
Is it possible to do the regression?
Yes. And this is what we're going to do next week. We're actually going to get a little bit of a taste of that today, because in R you can actually wonderfully do that, and it's super simple to actually put more variables in there. And it's actually, it becomes very interesting, because this is essentially then where you build then full models which allow you to really seriously estimate your dependent variable. And that's it's very easy to code, and it's very powerful in terms of insights that you can have. And for your final project, I highly encourage you to really think carefully about what additional variables you want to include if you build such a multivariable regression. The same with the logistic regression. And the logistic regression, you can also, if you're trying to predict the binary outcome, let's say you're predicting diabetes, yes, no, and you have a list of variables, you can easily include more than just one variable into your model. And you get an estimate of the probability of the individual being diagnosed with diabetes based on whatever factor you're interested in. So it's very elegant. It's a wonderful approach. You'll see. Any other questions? Thank you. Good question. If not, then let's quickly focus on variation. And it's not only variation, because it's this rest error, right, that you need to quantify. So why are you doing a least square fit? Why are you fitting a regression model through there? Why you deal with all of this to basically have now, in addition, you could just say, okay, so I predict my dependent variable by saying, okay, so it's equal to the mean of y. I could do that, right? Or the mean of y instead of x. So this is basically, as we remember from the quantification of the standard deviation, we calculated individual deviations from the mean. That gets us an estimate of all these deviations. Then we're squaring all these deviations. That gets us squared deviation. And then we summed up all these squared deviations, and that got us to a sum of squares. And this sum of squares we divided by the degrees of freedom, and we got to the standard deviation. First to the variance, then we square rooted it, we got to the standard deviation. So that's your total sum of squares. So that is y, predicted y, equals mean of y. That is your simplest way of expressing some variation in your data on the dependent variable, on the outcome variable. So that's the total sum of squares. So that is yi minus y bar. That's the total sum of squares. So now we're digging a little deeper. So now we have the sum of squares error. So what is that? That is now the individual data point of y. Subtracted from that, we have the predicted y. So that is your regression function, your predicted y, minus the individual data point. So you're predicting now for your entire population, you're predicting your y, and this difference is essentially your error. That's your residual. That's this error. And now you have, in addition to that, you have now the sum of squares of the regression per se. So this is kind of how should I say? This is the difference between the predicted and the mean. So you get now these differences between a mean, if yi is just the mean, minus the predicted yi's. That gets you the sum of squares regression. So the interpretation of that is this is the variation of the yi values around the mean of y. That's our total sum of squares. Then we have the variation of attributable factors other than the relationship between x and y. That's your residual. And then we have the explained variation that is attributable to the relationship between x and y. So that's attributable to the function. And now when you quantify what is called the coefficient of determination, or r squared, you're calculating the variation between sum of squares regression and the total sum of squares. So when you think about that, what does that mean? This difference is literally that variation that you have, how shall I say, you explained this variation in your data by fitting that models through. So when you look at this function, so this is the total sum of squares. So this is like all the variability you have in your scatter. That's the leftover variability of that residual error from your function to the individual point. And this here, this is kind of the difference. So if you only leave this unexplained variability away and you subtract this from that, you're left with an equation which would be SST minus SSR equals SSE. So that's the leftover error. So this is the variability that you have explained by fitting that function through. So now, keeping this in mind, this equation here is an extremely powerful equation because it basically, this is your explained variability and that's your total variability. So you're basically quantifying with this the proportion. So again, keep in mind how you calculate proportion. You have a smaller fraction. You have 10 people out of 100 people are diabetic. You have 10 divided by 100 gives you 10%, right? Or 0.1, and then multiplied by 100 gives you 10%. This is calculation of a proportion. So you basically calculate explained variability divided by the total variability. And you get a proportion of what your model has explained based off the total variability in your data. So that's a very powerful marker. And the closer this is to 1, the better your model is. If your model is closer to 0, your model is useless. So, and that's kind of, yeah, that's kind of the guiding star. You want to get that R square up. in your model. Of note, if are we seeing this here already? Yeah, so it's r squared or r yeah, r to the power of 2. In a simple linear regression where you only have like one dependent and one independent variable, you can basically take the correlation coefficient and square it. You cannot do that if you have more than one independent variable. Then you're not allowed to do that anymore because that doesn't work like that anymore. You don't have a correlation coefficient. Then it's being quantified a little bit more complex because then it's quantified using F statistic from ANOVA that we've learned there. So with, you remember we had between groups variance and within groups variance, and the ratio between groups and within groups variance gives you the F. And that F is then being used to do hypothesis testing, and you utilize essentially this quantification. Yeah, so you get a total sum of squares also for the ANOVA, and you calculate it in the same fashion, but you basically go there via using the principles of F statistic. So it's a little bit more complex in a multivariable model. Okay, so R squares between 0 and 1. The closer to 1, it's good. The closer to 0, it's not so good. Good. Any questions on this? I think that's super important concept because if you do correlation and analysis, you will need to state and you will need to present an R squared. So I think it makes sense to kind of a very solid understanding of what an R squared is. So sum of squares explained by the regression divided by sum of squares in your entire data. In the single independent variable case, the coefficient of determination equals correlation coefficient squared. Good. We talked about this. Good. Any questions on this? No? All right. Yeah, so R squared, an R squared of 1. If anybody shows you an R squared of 1, he or she is lying to you. Doesn't exist. In real life, with real data, you will not see that. I've seen that once in a, yeah, I've seen once a journal article that I was asked to review, and they reported an R square of 1. That was the only time where I said, like, I'm not reviewing this paper anymore if they don't send me the data and I do the analysis myself. So it's yeah. So you will not see an R square of 1 in any real world example. I guarantee you that. If you do, please shoot me an email, and I want to see that. I really want to see that. Okay, good. So 100% of the variation in Y is explained by the variation in X. Yeah, so the weaker the relationship, the smaller the R squared. Yeah, no linear relationship. Again, with regression, we're testing against Y equals mean of Y. So your null hypothesis is a flat line. So assumptions. And assumptions are, yeah, the assumptions are kind of comparable to those in ANOVA, particularly in terms of variability, normal distribution, and independence. So we're assuming that there's homoscedasticity in the data. That means that the variability in your data is the variability of the Y values are comparable across the entire magnitude of the X variable. So the variability of your dependent variable is comparable at all levels of the magnitude of the independent variable. Not always true, unfortunately. You will see that quite often, but that's why it's important to really map out a distribution table, right? That distribution, that you look at the distribution by basically plotting it as a scatter plot. Because you also get a feel for the distribution. You understand your data. That's why descriptive statistics are also so important. So basically, homoscedasticity is basically important. Here it is shown and described as the standard deviation of error values. So your epsilon is constant across values of x. What does that mean? That's basically what I just said, just more specifically targeted towards the regression function. So basically, when you have residuals and you have this distance of the individual data point, what's this now? Right here. So these distances, these residual errors, should be more or less the same across the entire range of x magnitudes. And we will look today at diagnostic plots of regression models that will allow for us to understand how these residuals distribute. That's actually particularly when you do multivariable models and you do logistic regression or you do Cox regression, this is super important. So this is where you test whether these assumptions are being met. So homoscedasticity, it's kind of an elaborate, more elaborate extended version of the assumptions for ANOVA, where you remember the variance of each of these groups shouldn't exceed more by like 20% from others. Then you have an approximate normality. This is more of a rule of thumb again, but you need to understand that your data is more or less normally distributed. Then you have independence, so that's important. When you do construct scatter plots, each of these data points needs to be one individual. So this needs to be a pair of data for one individual. So when you remember the immunization example, what's that now? Each of these data points is one country. And that's the independence of your data points. So that's extremely important. Yeah. So independence, homoscedasticity, normality, independence, and linearity. So it needs to be a linear relationship that actually only then it makes sense to fit a linear function through that. If it's a nonlinear relationship, you're basically, you won't see the association, you won't see a true association. So if you have a nonlinear relationship and you fit a linear function through that, you may still see an association because there may be some numerical association, but basically you are most likely running in a type 2 error pattern. So basically using inappropriate method for quantifying that should be quantified with a different method. Okay, yeah. So the way you would present this, and this is the mathematical way of presenting this. So you have your y variable, your dp number variable, as beta 0, which is your intercept, plus beta 1 multiplied by x, that's your slope, and your individual x, or the x variable, and then each individual x, plus epsilon, where epsilon approximates a normal distribution around the mean of 0 with a standard deviation that actually should be variance. Usually it's sigma squared. But yeah, it's basically, it has a distribution around the mean of 0. The link between correlation and regression, and this is where it's getting a little complicated. I don't want to go too deep into it, but basically when you take the standard deviation of y divided by the standard deviation of x and you multiply it by the correlation coefficient, you basically calculate your slope. So this is arithmetically, if we would go back to the correlation coefficient, if you standardize these associations, you're getting them to a standardized coefficient and can utilize this to multiply this by the correlation coefficient, getting to the beta. But this is too much detail. Yeah, so this is the standardization. So you calculate the set score and then you utilize this to essentially transform it. Okay, so this is just an example. So you have the relationship between weight and height, and we have calculated the body mass index, right? Why did we do that? Because in most cases, this is not really a linear relationship, although this implies it is one. It's usually not a linear relationship. You basically, when you quantify weight and height, taller people are heavier because they have bigger bones, they have more muscle mass, they have various parameters. So basically, there's an association. And this is how most statistical software will show you that data. And we will look into R codes that basically shows you, or R output that show you exactly that. You get an intercept which is an estimate of the intercept. Remember, intercept is the y value at which the x equals 0. So we are 150. So if you continue all the way down here and you're hitting 0, that is your intercept. Your slope is the increase in the dependent variable weight with an increase in height. So with each centimeter of increase, you will get 1.0176 kilograms of increase. So with every centimeter you're taller, you have 1 kilo more. Do we believe this data? But again, okay, but let's stick just with this interpretation. So basically the way you would utilize this, you want to know, you want to predict the weight of an individual that is, let's say 170 centimeters, let's do 180, that's easier. 180 centimeters, that's 5'10". You want to estimate the weight of an individual that's 180 centimeters tall. You basically take the estimate, the minus 105, and you take 180 multiplied by 1.0176, and you add these two together, and that basically gives you the estimate of the weight. That's how simple it is in simple linear regression. So that's, somebody has a calculator, 180 multiplied by 1.0176. That's somewhere in the realm of. That I doubt. You mean both together? So it's minus 100, and I would more say it's somewhere in the realm of like 90, 88, 90. I don't know who has calculated quickly, but it's like, yeah. So it can easily be calculated like that. You would multiply 180 with height, with that estimate for height, and then you subtract 105 from it. So if you do this, it's like you have here 180 multiplied, that's like 8. That should be somewhere in the realm of like, no, it's actually not that much, 18. There should be somewhere in the realm of like 185 minus 105, that's 183 minus 105 now, so that's 78. Yeah? Okay. 78? Okay, good. Thank you. Okay, then we have the standard error. The standard error is now your standard deviation around that estimate. Follows a t-distribution, right? We remember. Then we have a t-value, that's the t-distribution. And then we have a p. And the p is our probability that this is actually significantly different from 0. And this is all that needs to be interpreted in a simple linear regression. Good. Continuous outcome, continuous predictor, Pearson correlation from -1 to +1, R squared from 0 to 1, the proportion of variance explained by the regression model, regression coefficient related to R. So you can, by quantifying the standard deviation of y divided by standard deviation of x, you multiply it by R, you calculate that slope. And why can you do that? Who of you can remember from, I guess in high school, you must have learned that, how to calculate the slope? Do you know how to calculate the slope? The formula. Now that's the regression function. That's a function for a line. No, only the slope. Okay. Okay, so you have. I don't want to sidetrack the conversation too long, but I think this is just a funny example because over correlation inversion. Here we go. Ah, oh, here. So if you look here at a completed spreadsheet, so okay, let's just, okay, so that was an example I did with my undergrads in spring. Okay, so you have the back depression inventory score. That's a survey. That's a survey quantifying depression. It's one of the oldest surveys that's around. It's the number of stressful life events. So you get your regression function. So let's say you want to estimate your slope, and you want to estimate that slope. You can do this essentially by calculating. If I have here, let's say here, this is like, I want to have this slope of that function. And I'm saying, okay, so here it crosses at 1, it crosses somewhere at like, let's say 13 at 1. So my y, my y2 is 13. My y1, so my second reference point for the dependent variable here would be where it goes through the intercept. This is my y1. So that's like, let's say 10, which I always know from here, right? So it's y1 is 10. So now I want to know an x2. So that's the higher value of my of my x variable. So that's 1. That's this one. And then my x1 is 0. So with these variables, I can calculate now the slope by calculating the following formula. So slope equals y2 minus y1 divided by x2 minus x1. That's a way how you can calculate the slope from here to here. So y2 minus y1, that's 13 minus 10, that's 3, divided by x2, which is 1 minus 1, and 0, so divided by 1. So it's 3 divided by 1. That's the slope that I'm seeing here in this regression function. So that's how you quantify a slope in any random graph that you would see. So whenever you see a line like that, you can hypothetically estimate it. Brings me to another point. Some of you may find it helpful, actually. Okay, let's do the following. You know how to do screenshots. If you do on Mac a screenshot, I'm going to show you now a very useful tool. So it's called Web Plot Digitizer. Web Plot Digitizer is a software that is online that basically allows you, free of charge, totally free. If you go here and launch now, you basically have here the opportunity or the possibility to copy a random graph that you screenshotted. So if you do here Command V, it puts in my my back depression score. You select then what kind of graph that is. If you say this is a 2-day XY plot, you basically let WebPlot Digitizer know this is a graph that you copied from somewhere. Then it prompts you here to quantify X1, X2, X3, or Y3, and Y4. So these are the points it needs. So you tell WebPlot Digitizer, this is my 0. You say, this is my 6. You say, this is my Y1, and this is my Y2. Then you say, complete. Then it will ask you, okay, so that X, that first X that you gave me, what is that? That's 0. What is that second X you gave me? That's 6. What's that first Y that you gave me? That's 0. What's the second Y? That's 35. So if I go on OK now, I basically activated the graph. So now what you can do now, you just go click, click, and you see how it zooms in over there. Click, click, click. And now you go on view data. And it gives you the actual data points. And it calculates automatically where in the graph that was positioned. So it gives you an actual data set. You can export this then as a CSV, so you can digitalize graphs. It's quite a powerful tool when you have, let's say you have a paper of, it's obviously it's more smaller studies, right? It's like, if you have an epidemiologic study with 100,000 patients, it's like, good luck. But basically, if you have a smaller study and you want to quantify some data and you want to play around with the data, that's the way to do that. So it's just a fun gadget. Okay, enough about that. Any questions? Then let's get started now. Okay, so we have, do you have any questions concerning anything that was done last time? Any questions on the created lab that's submitted to be tonight? No? Any general R questions? Any roadblocks that you have come across? I guess there are many, but it's a learning curve. It's a learning curve. Just a learning curve. Oh, no, just the learning curve. You'll get better and better and better. Okay, so we have practice lab number 9 today. We have 45 minutes left, so that's ample of time. So we will do a couple of GFR. Okay, forget eGFR. That's a different data set. So we're doing today, we're loading a data set into R. We're testing data for an association between age and blood pressure. So patients, as they age, their blood pressure will increase because they're more likely to develop atherosclerosis, except for women before menopause. So we're quantifying this relationship in the overall population and then between men and women. And we're plotting the regression function and R-square for the overall population for males and females. So we're looking at a scatter plot. We're fitting a function through that, and we will then calculate an association between pulse pressure and age. So pulse pressure is basically calculated as the difference between systolic and diastolic blood pressure. So this is essentially, I'm not going into the hemodynamic details, but basically this difference is basically a reflection of arterial stiffness. So this actually, if this is larger, that's a sign that the vessels, the circulatory system is a little bit stiffer in that individual. Then we do mean arterial blood pressure, which is here the Bassett's formula shown. So I basically do these exercises with you because it allows for you to do some calculations in R and to learn how to do these calculations, and you're not shying away from doing calculations. And then we're gonna do a multiple regression, but that comes later. Good. Load the data set into R. So there is a data set that you have at your disposition. This data set is basically containing variables. It contains blood pressure, age, and gender. That's all what we essentially need for this exercise. So, we need the path name of this data set. And copy this path name. And we need to open that R code. Okay. So we have here the practice lab 9 R code. It's on your module. Just need to copy the path name. You can just load the data set. Good. Okay, so the ask is to first load the data set. You know the drill. You need to determine your folder in which the data set resides. Please download the data set from Canvas. It's today a different data set than it used to be last time. You can now, as a next step, you're loading this as a DF into your environment. That has happened here. We can now take off this one column that nobody needs. That is basically done with line 4. How many variables do we have here? 6 variables. We're undertaking 2 to 6. So we're deleting 1. We're not deleting it, but we're basically transferring it on, and we're dropping 1 variable, which is the first one, which is this annoying column whenever R imports in CSV file, it keeps this 1 running number in front. It's like, I don't know why R is doing that. I don't know, Natalia, do you have experience from Python? Maybe? Python isn't doing that, right? When you import a CSV file, does Python create this additional row? Okay. No, because this is so annoying. It's like you basically see this always. It always shows this one row, and I never really understood why. So there's always this X. Nobody needs this X. We'll never understand why it does that. But yeah. Okay, so with line 4, we're killing that 1 variable. We're dropping it off. We're only working with 5 variables, 1,000 observation, 5 variables. We are now basically creating a new variable, which is male. So we're creating male gender, and gender is basically included as either 1 and 2. It's an enhanced data set. It's basically the enhanced experts and the CDC analysts, they like SAS. That's why they do everything in SAS. And for some reason that is absolutely mysterious to me, SAS insists on coding binary variables in 1s and 2s. And it's beyond me why SAS is doing that, but it's kind of the standard. So every SAS analyst will code this into 1 into 2s. So as soon as you get a SAS data set, make sure that you understand in which way this is coded. So we're recoding this in male gender, which is either 1 or 0. Then we're transforming this into a factor, as we've done in the past. And please pay attention here, because we're doing here male and female, and we're doing levels 1 and 2, which is utilizing that very structure that the original file has. Okay, now when we do summary, we're seeing that we have 479 males in our population and 521 females, which adds up to the 1,000 observation in the DF. So now we do some hypothesis testing. So we basically want to see, okay, so are there differences between males and females in terms of blood pressure? So that's line 11. And male is not found. Okay, because I didn't run this. Okay. Okay, so line 11, you need to please run 6, 7, 8, and then go to line 11 and run line 11. And with line 12, you're basically looking at this comparison. So this comparison basically compares men against women in terms of their blood pressures. And we're basically seeing, indeed, we're seeing a difference of 4.3, 4.3, give or take, with a 95% confidence interval, which both upper and lower bound are negative. That means there's a significant difference, which is confirmed here by the p-value, with degrees of freedom of 991, and we have a t of minus 3.7, indicates a significant difference. So we know that there's a difference. What is going to happen if I'm using this now in a linear regression? And that's kind of interesting, because if you include a binary variable in a regression model, well, this is actually, it's a little early to show you this, but you can basically, it uses F statistic, right? So it's quantifying means and the variance between means using an F statistic. So we'll do hypothesis testing for you. So you can basically, you can use a regression model to do hypothesis testing for you. And we're doing this on line 13. Oops. In line 13, we're running a regression model that basically will now quantify an intercept. So remember, you have in a regression model, you have a coefficient which is now tailored to either to your X variable. So you're predicting systolic blood pressure as a function of a binary variable, which is either 0 or 1. That means if X equals 0, that X is basically falling off, and all that's left is your intercept. And your intercept in that case is where is basically the mean. It's the mean of those where male equals 0 or 1, but it's the mean of those where male equals 0. And that's women. And that's 122. And if you look at the t-test, the intercept in the regression model is consistent with the mean in group 0. If we add to our intercept 4.72, we have established the mean for the group where male equals 1. So this is the beauty of the interpretation. So if you have 0 or 1 in a categorical variable in a regression model, you can estimate the difference between your groups in your regression model. But we'll do that in more detail next time. But that's just a first taste of how wonderful regression actually can be used in various use cases. Okay, but let's carry on. This was just a first taste of what we're doing next week. So if we're going now to line 17, so the first ask is to calculate the association between age and systolic blood pressure in the overall population. So R basically gives you three different ways to quantify a correlation coefficient. And I'm not going to go deep into what these three different methods are, just as much. Pearson and Candle are basically for parametric testing, and Spearman rank is basically a non-parametric test that you can use for non-normally distributed data. The only reason why I'm showing this is for you to understand how important it is to test, to look at the functions with question mark and function name. You can basically always review the function, and you can look into what else is that function offering me. And for this particular function, you have, as just for starters, you have different methods that you can use. Excuse me. You have different methods that you can use. So you get a correlation between blood pressure and age using Pearson. There's a correlation of 0.48. Keep in mind, correlation coefficient goes from -1 to +1. The closer it is to 0, the less of an association there is. So 0.48 is actually not that terrible. I think as per Cohen's definition, this is a large correlation, or at least medium. Okay, Candle gives us 0.43. Spearman, equally generous as Pearson, gives us 0.48. So we can conclude that there's an association, right? If we want to build now, and this is as easy, correlation is done as easy. You have DFSBB here as the first entry. Actually should be different. It should actually be the second one, because age is actually the independent variable, whereas blood pressure is the dependent variable. The way you would arrange this is usually X, Y, and then the method. So this is actually wrongly arranged by me. Yes. Excuse me?
Is this not running? Is this running? Yes, it's running. Yeah, Candle is running.
Candle is not running?
Yes.
We're just gonna run one after another.
Show this question mark.
Now you have the question mark first. You just gotta run. Yep. Okay. Everybody on pace with me? Good. All right. Next. Okay. Linear regression. Linear regression in its simplest form, you run with the LM function. You're packing it in an object. You call that object fit all because it's all the patients. That was very innovative in the variable labeling. So we have LM SBB tilde as a function of age, and the data set is DF. That's how simple the syntax is. And doing this basically builds you your first linear regression model. You can call this, and we've done this earlier, but with summary, you're actually getting to the beef of that model. And when you do summary, you're basically seeing all this wonderful information that you get from R. So what do we have here? We have the formula, which we know. We have our residuals. Remember, residuals is the distance of the individual data point to the regression function, to the line, the least square fitted line. We have residuals that are shown as min, max, first quartile, third quartile, and the median. What are we missing? Yeah, what is the second quartile? Yeah. So the median basically denotes 50% of the data. So we know that the first quartile would be min to first 1Q, so Q1. We have Q1 to Q2 would basically be the second quartile, median, yeah. Q2 to Q3 would be the third quartile, and Q3 to max would be the fourth quartile. But when you look at this data, wouldn't you like to know the mean? Yeah. Yeah, and why don't we have a mean? Is what? It's continuous. No, but why don't we have a mean? What do we know about residuals? Exactly, the mean is zero. The mean is zero, correct. That's why it's not even listed here, because R is assuming that that the user knows that the mean is zero here. So when we compare a mean and the median is minus 2.9, 2.23, minus 2.3. In which direction is the mean? What's the skewness? You had a 50-50 chance, that was the wrong one. It's positive. because you have outliers to the positive, the median doesn't react to outliers, right? But the mean is pulled to the right. But the mean is zero arithmetically because that's how it's derived, right? But the median is rock stable where really the bulk of the data is. Okay, so would you be concerned about skewness? Well, the max is kind of wide, right? But this is exactly the eyes you need to, the magnifying glass you need to put at these outputs, because this gives you a lot of understanding of whether the assumption of homoscedasticity is met, right? And we will look at the diagnostic plots where we can really investigate this in more detail. Okay, coefficients. The coefficients are the same ones that we basically would be expecting, and we've seen that with the height and weight example. So we have estimates, we have intercept. Okay, that's the 101. What does that mean? What does 101 mean? What's the interpretation of that? Correct. What is that in a little bit more described?
When age is
Correct. So a newborn has a blood pressure of 101. Correct. Yes. Okay. Good. So with every age, with every year of age, that will increase. A 20-year-old has an blood pressure of 120, 110, 111. So we have a standard error. We have a t-value, it's t-distribution, and we have a p-value that basically indicates a significant relationship. Good. All right. So very good. Thank you. Good. So now next we go fit males is LM SBBH as function of age. Yeah. So now we want to have only men. So now males or gender equal double equals 0 will basically give us this. Don't remember that when you want to subset your data frame, your DF, you need to put DF in brackets, and here place a comma. Everything before the comma will basically restrict the rows. Everything after the comma, you can then alter the variables you're interested in. And we want basically all the variables of DF. So that's why we leave it blank. And we only want those rows, that's before the comma, where gender double equals 0. So that will basically be this list. If we just run this part, that will be only our males. And you see here that these numbers are discontinuous because in between you had the females. So it only selects the males out of that whole data frame. So when you run this linear model, you do fit males, LM SBBH restricted to gender equals 1. You basically only get the fit in males. What do we see? In males, the intercept is larger. We had 101. Now we have this larger. Well, I'm not doing summary. Okay. Line 27 runs the summary. So what do we conclude out of that? Men have higher blood pressures, which we know. Good. Fit females, same story. Now gender equals 2. We can also do summary. So now in females, this estimate is 20 millimeter Hg lower. So that's quite a massive difference, actually. It only gets larger with age significantly, and we will look into subsets of that next time. Today we won't have time, I guess. Okay. So this is how you do linear mixed effect, linear mixed effects models, yeah. Linear regression in its simplest form. If you want to quantify now that association and you want to show it on a scatter plot, you would do this with the plot function. Oh, well. Okay. This is a little bit more of an involved code. Why did I do that? So basically with lines 34 to 35, you're creating the framework of that plot. So you're just creating the canvas on which you're gonna draw your plots in a bit. So doing this, you're saying here, I want a plot spanning over 4 different values, which is the minimum of age, the maximum of age on X, and then here's another C, the minimum of SPP and the maximum of SPP. So basically you create those boundaries. So you say, okay, take the minimum of age, take the maximum of age on the x-axis, take the minimum of SPP and the maximum of SPP on the y-axis. So it just creates that framework that looks then essentially at the end of the day. So color white, that color age at XLab and YLab, we talked about this already. We know that. So now what we get here, this is our empty shell of our scatter plot. That's just creating the boundaries, creating that plot in a way that we can now fill it up with points. which we're doing now in line 36. On line 36, we're subsetting our data frame again for females. We're taking now the factor variable. We're saying, okay, so give us on the x-axis, give us the age entries for all the females. And on the y-axis, give us the SPB values for all females. That essentially creates a scenario like this. So that plots now all our females in terms of blood pressure and age. And yeah, so I made it a little bit more aesthetic here. So I'm not good in graph aesthetics. I'm just saying, it's like whenever you get a graph from me, it looks either utterly boring or quite difficult to interpret. So that's not my forte. Never been, will never be. So if you zoom out a bit, so we have basically now the females depicted with red triangles. So you can change, you can actually play around here a bit with it. So PCH changes the point, so it changes the shape of the point. So feel free to play around and use a different shape. CEX, so CEX is basically giving you, it's giving you a changed dimension in reference to 1, and 1 would be the default. So CEX equals 0.6 basically makes it smaller. If you do CEX2, then you have like a huge point. So you can change the size of the point. With COL, red, that's yeah, that's the color. PCH is the point, the shape of the point. If you do question mark PCH, yeah, if you do question mark PCH, it basically automatically pops up, and PCH, it basically gives you here a list. No. CX core. Oh yeah, here. No. Yeah, here. So here's an overview of all the shapes that R has to offer. So you can use various. So the higher you come, you even get like runes. It's like, I don't know what order it is. So you get like a lot of different shapes. So now feel free to play around. You get solid, you get filled, non-filled, so you can use various symbols. Good, but we want to focus now on our males. So if we go on line 37, we're adding now our males. And so now we have basically all of these data points on one graph. Looks super busy. And now we're doing the next step. We're building fit lines that basically go all the way through and basically fit into our scatter with a least square approach. So this is done with LM female and LM male. You're building two new models. You're building a model between systolic blood pressure as a function of age in males and one in females. You're utilizing then these estimates to use Airline. So you build these two models. You use Airline to basically grab this model and use it for the prediction of the regression function and depict it on your scatter plot. So Airline 40 and 41 basically builds now these models and fits them through as regression lines. So that's the least square fit line. So you're doing that with these commands. Good. And then lastly, on line 42, you're adding some text. And the text you're adding is x equals 25 and y equals 210. That's basically x, you go on the graph, you find on x25 and you go all the way up to 210. You will implement some text, and the text it pastes with labors paste R2 equals a rounded fit of your fit or with an R squared. You're basically depicting this now on your graph. And that's how that will look like in the end of the day. So those of you who are right now doing the intermediary R, you will learn about ggplot2, makes much prettier graphs. These graphs are basically the base R graphs. I like them. Many people don't like them. So, but feel free to utilize ggplot. It's like, it makes prettier graphs. Yes.
How can we really this that this plot? Because we know the blue and the red, like the line that is being drawn, how is it generated?
This line? That's line 39. What was it? 40 and 41. App line. This command here. 40 and 41. This basically utilizes the model built in 38 and 39 and fits it through that scatter. Yep. Okay, so now we're doing the same thing for males and females. Now we do 3 different plots. So now we're doing the same thing in black. That basically builds now a separate model. So the association is less strong in what's this, males? Yeah, males. Yeah. So in males, the association is 0.11. And in females, it's 0.36. So the association between age and blood pressure is actually stronger in women than it is in men, because men start off with higher blood pressure. Somewhere in this, that word, that explanation. So now we want to inspect the first model fit. We looked at this summary. We looked at this. Now we want to dig a little deeper. So I told any questions about any of this so far? I think it's in terms of coding, it's considerably simple, right? It's really not that complicated. So you have now with fit $1 residuals, you can basically investigate the residuals. Remember, a residual is the difference between the individual data point and the predicted data point of your function. So basically, these are basically all these 1,000 entries minus the predicted value corresponding with this individual entry. So you can basically depict this as a data frame, you know, or as a vector, more accurately spoken. If you take your fit now and you run line 58, you basically get your residual plots. And now this is now getting interesting. So this is one of these diagnostic plots. So we're basically getting now our fitted values, SPP versus age, and this is our blood pressure. And these are the residuals. So what do we want to see here? We want to see a straight line because we want to have an homoscedastic relationship, right? No relationship. There's no relationship we're quantifying here. This is a prediction over the entire range of predicted values and the associated difference between the individual prediction and the observation. And these residuals shall not change over the entire magnitude. If we're pressing enter here, we're getting to another residual plot. No, we actually don't. Why not? Okay, now we did. That's another way of looking at this. So we see now a little bit of an association, a little bit of an increase because we're standardizing them now. So we're standardizing them now. We're square rooting and standardizing them. That's a different way of looking at this, but basically it has the same inference. These are residuals versus leverage. Leverage basically is how much does it actually play an effect in the model estimate. So we again see a considerably flat line. So basically independent of the leverage of that particular parameter, it doesn't really affect the model. So these are the residual plots that R readily provides to you. Also, if you do summary fit one, LS summary fit one, you get a list of things that R can show you from that fit one. So if you have adjusted R squared, you can address each of these variables components in the model by basically approaching them with summary fit one, $, adjusted R squared. You can pull out the adjusted R squared from right here. So you can address these and R will spit those out for you. That's what we did up here in the graph. So we basically adjusted R squared, and we pasted it in a text field on the plot. Good. So yeah, I did deviate here a bit. You can also play around here. So you can basically look at linear regression. You can calculate the blood pressure now at a certain age. So you can basically utilize these actual coefficients. You can extract them from the model, and you can utilize them to actually calculate your actual value. So if you want to have the SPP at 50, you basically can calculate it by taking coefficient 1,1, which is your intercept, and then you take 2.1, which is our slope, multiplied by 50. Remember, the regression function is intercept plus slope multiplied by the individual value. So if you multiply the slope by 50 and you add the intercept, you basically get the estimate for the blood pressure at the age of 50. So now we have the calculation of the pulse pressure. That's basically SPP minus DPP. We can do a histogram of that. That basically shows a comparable distribution of the SPP. So you see positively skewed distribution, but considerably normal. We can plot this now as a function of age. And we see, well, almost like a nonlinear relationship. But for the sake of argument, let's just continue by approaching it in the same fashion. We do a linear fit. We can now look at a summary fit one. Summary fit one shows us now, again, a significant relationship with pulse pressure. And here, line 76 is now adding to the previous code, where we basically were quantifying the confidence intervals. So we can quantify the confidence intervals from our linear model, where we basically get the upper and the lower bound of our confidence intervals around our estimate of age. So the way you would look at this, you have the estimate in the model, which is for age, it was, what was it, 0.5. And the 95% confidence interval is here 0.45 and 0.57. So then we're just doing the same thing here. We get a text implemented, so that's pulse pressure. When it comes to data reporting, I just quickly want to show this. So I've shown the paste function. Any questions on any of this? I think if you go step by step through the code, it will make a lot of sense. I think it's considerably intuitive. If you go for data reporting, you can utilize R to do the data reporting. It's quite a convenient way to do that, particularly when you transport it into an HTML document. So please, I didn't state it on practice lab, please transfer it in an HTML document in R Markdown. So if you run line 84, oh well, that looks terrible. So you actually should be rounding that. So this is a mean estimate of the SPP plus minus, and this is indicated here between those two quotation marks, the standard deviation of SPP. You can actually also round that. Let's do some rounding here. So with the round function, you can round this. Comma 1. Let's also round this one. It's just nicer when you have. Okay, that looks better. So with the round function, you can quickly round this. If you want to express it as a median, so that's line 85. You basically have here the median of SPP, which is 122. You have then brackets surrounding the 25th and 75th percentile, which you essentially get out with the quantile function, and then you can express it basically here in one line. So that's how you would present it in your final report or in any further paper down the road that you're going to be writing. So this is like the most accepted way how to express central tendency and variability. Lastly, now we're looking at the estimate of age from the linear model. So you basically you get an estimate of your coefficient, that's a slope coefficient, beta 1. You get a 95% confidence interval, which is expressed here in quotation marks. And then you get an estimate of the lower bound and the upper bound. Basically, you're extracting this from the conf_int function, where you take the object name, the model name, and you're expressing this with conf_int. Just like we did on line 76. Okay, so this is how you express data. Then we have the calculation of the mean arterial pressure, that's on line 90. Again, whenever you calculate something, R will basically, like consecutive, in a consecutive fashion, go one by one through all entries that you have in your data set. So if you tell R, I want to create a new variable, MAP, and I want to utilize each entry of SPP, and I want to, excuse me, it's a good air conditioner in here, multiplied by 1.3, 1 over 3, plus 2 over 3 multiplied by the DPP, R will basically go to the first row, grab the SPP value, grab the DPP value, do this arithmetics, and then put this row in the third variable. And it will do that as many rows that there are. It will consequently go through each row. So that's how you can calculate that. And then you can hypothetically do now a histogram and look how the MAP looks like. Oh, what am I doing? Here's DF $MAP. So that's how the MAP distributes. Of note, this is really a nice normal distribution. So this is how MAP distributes. You can now utilize MAP to look into the association between MAP and age. And you will see also here, you see an association, a significant association with age. So as a little bit of a background, mean arterial pressure is basically quantified as a means to kind of incorporate both SPP and DPP. I'm just putting this in there to calculations, but it's used quite frequently in epidemiological studies. So lastly, we want to know how these two basically interplay. And now coming back to Natania's question, can you include more than one variable? Yes, you can. And you can do this quite simply. And this is the exercise where we continue next week on Wednesday. We will build more models. We will look at a bit more deeper into these models. So basically line 96 to 99 gives you a first taste on how to do that. So we have the gender factor we did already. So basically what you do here, you're building just with the same function, you build a linear model. You do it as a you do the dependent variable as a function of age, which we did before, but now you include with a plus sign you include the second variable. So it's really that simple. And once you do that, you basically build your model, then you can look at the model and do interpretation on the model. What becomes interesting here is that it gives you a different formula, same dynamic with the residuals. So you basically get the same description of the residuals, and you get now estimates for each of your included variables. So the intercept is smaller now. The intercept is now only 83, but what was added in here is that you have age. So with each increase in age, you get an increase in millimeter Hg blood pressure, which is here with 0.2 smaller than it used to be with the previous model. And that indicates why it's so important that you're very diligent and very careful about including variable, because there's a tremendous effect of included variable on your initial estimates. So you know there's an association between age and blood pressure, but this is strongly affected by the inclusion of variables. So that's where the explanatory component comes into place. So you need to be very diligent and careful about what you include and how you include. So if you including now factor female, you're seeing now a factor. So if the individual that you're studying is not that you're investigating is female, you will have in your overall population, accounting for age, 5.8 lower blood pressure. And it's important to keep in mind a regression model, a multiple regression model is an additive model. That means that each of these estimates adds up to a final estimate of your dependent variable estimate. All right. So now, and that's also an additional. So now we're actually getting closer to looking at what I mentioned before with the F statistics. So you have a residual standard error now. So that's really your residual standard error that you see, which is that's the leftover error after you subtracted the predictive accuracy of your regression model. So this is SST minus SSR is SSE. That's the rest error. That's this guy. Out on 997 degrees of freedom, because we have three variables of intercept, age, and gender. So this is 3,000 minus 3 is 997. You have a multiple R squared, which is 0.10. So that's not groundbreaking. So you won't likely get the Nobel Prize for that. Adjusted R squared is now an R squared that is penalized for the inclusion of additional variables. So we will see the equation of how this is penalized next week. And it reduces the R square estimate. Because the R square has one feature, which is as soon as you include more variables, your model arithmetically has to predict more. It has to predict more of the variability. Thereby, your proportion of predictive error, or predicted variation, I should say, is getting larger relatively. So that means you include additional variables, your R square will always go up. The problem is if you include now more and more variables, you basically want to account for that you included so many variables. And you do that by adjusting your R square for the number of variables that you're adding. So that's the adjusted R square. As for the rest, we have now an F statistic, which again is the between groups versus the within groups variability, which essentially we're getting to next class. So this is 57 on 2 and 997 degrees of freedom with a p-value that is overall significant for the model. So this is additional information that now R is providing to you. All right, Rand's 3 minutes over. Any questions? The histogram, that's the mean arterial pressure. We calculated it here, line 90. Let's go one by one through each line. You'll find it. Any other questions? All right, regression is fun. I think you're gonna like regression. It's a very fun method to use. All right, if no other questions, have a nice evening. Have a good class after. Yes.
It's about the digital lab.
The what? The created lab?
Yes.
Okay.
The last part. The last part. Right.
Wait, let me stop the recording.